Hi, everyone. My name is Ayelet Lejtman. I'm very excited to be here today, so thanks for the invite. I have been working at Meta for 5 years, and I was one of the original engineers at Meta Shops, which is the Meta e-commerce initiative. And today I want to talk with you about our journey to establish product embeddings for shops. Okay, so let's start with some fun facts about e-commerce. Today, there are more than 20 million e-commerce sites across the globe. In 2040, 95% of all purchases will be through e-commerce, yet 46% of American small businesses still don't have a website. And that's also why Meta is investing a lot of efforts in shops. Okay, so what is Shops? Shops is a way to create an e-commerce website inside Facebook or Instagram. Maybe some of you are familiar with Marketplace, this tab at Facebook where you can shop secondhand products. So Shops is like this, but it's actually a B2C product where vendors can create a shop inside Facebook and user can shop on sites directly. Here you can see an example of an Instagram shop. On the left is the Lejtman wear shop, and you can see the brands and some products it suggests to the user. In the middle is the product page, and on the right is the checkout page. So what's so special about e-commerce at Meta? Why not just using Amazon all the time? So in my opinion, the Meta family of apps is all about social interactions. And that sets a unique opportunity to create a social e-commerce ecosystem that other e-commerce sites can't provide. For example, let's say I'm following a great cocktail bar next to my house, and it just tagged the new type of gin I didn't know about before, and now you could just easily shop it on site. Okay, now that we understand what is Shops and why Meta invests in Shops, let's understand what was our team mission. In Shops framework, we have interactions between buyers, products, and sellers. We wanted to create a set of features that will improve downstream tasks of all these entities. Examples of such downstream tasks are frequently bought together, provide the most relevant products, or recommending of a shops. We came to the conclusion that the most elementary building block for such features is building a similarity between products. And to that end, we needed embeddings. So what are product embeddings? So embeddings are a way that we can represent products as a points in Euclidean space, and similar products will appear closer to each other. Why not using just a naive representation like pixel of the image? So I think a very simple example of why not using raw pixel is that if we have exactly the same dress, but in a different image, in a different color, they will appear far from each other and we'll not know that they're actually similar, while good product embeddings can put them in a similar area and space. How do we use the product embedding? So a typical application of these embeddings is to use it as a retrieval of similar items using nearest neighbors algorithms, and also by using it as an embedding as a feature in other ranking models. Okay, so we want to construct an ML model to train embeddings. What we usually need to build a good ML pipeline, we need the data, we need the features, we need model and losses, offline evaluation, and hopefully also some customers. But in the beginning, we didn't have those. We had no data, no model, and no customers. What we had were pre-trained image and pre-trained text embeddings that we just concatenated to each other in a way that similar items that had similar image and similar text embedding appear closer to each other in space. Why do we need a baseline? We wanted that for evaluation and comparison and understanding of our problem. After having a baseline, we actually wanted to push as fast as we could to production. And this is why we needed to build our model in Meta's infrastructure so we can calculate our embeddings on billions of products. This also required a lot of effort, and this work was done in parallel to creating all the data sets and features I will just talk about. So what was our first data set? We built categories triplets dataset. Triplets are actually 3 products, anchor, positive, and negative, where the anchor and the positive should be similar more than the anchor and the negative. But when I say similar, it actually depends on the context. And in this dataset, the context was categories that were inferred by a different model. So in this example, you can see 2 dresses as an anchor and positive and a shoe as a negative product. And in the end, they should put the two dresses closer to each other in space. But why using triplets for embedding? So I think that there are two main reasons for that. One is that embeddings try to learn relation rather than absolute values. And triplets does exactly it. It's not explaining what the item is, it just tries to capture the relation between the products. Another advantage is that this is a much simpler task. Imagine you need to annotate triplets compared to annotating pairs. It's much easier to decide which product is more similar to the anchor comparing to deciding if two products are similar to each other or not. Okay, so we had our triplets, but we had to create some features that will represent them in the model. So we used the pre-trained embeddings I mentioned before, the pre-trained image embeddings and the pre-trained text embeddings. Actually, the pre-trained image embeddings proved useful as they were trained on commerce datasets, while the text embedding weren't. We used a PyTorch to write our ML model, so we could easily change weights and layers and so on. Okay, so as I mentioned, the first step was creating a simple model that you can just push to downstream tasks. And that was amazing because the shops ecosystem was actually starving for any commerce-related signals, and we managed to push our models to production in several use cases. And this way, we could learn and understand better our users. For example, we could understand what's the category they're most interested in. You can try and guess, is it fashion, electronics, kitchenware? Okay, probably all guessed kitchenware, so let's look at the fashion as a case study. Let's start with our first triplet that we built, which was based on price. Why? Because we don't want to recommend a wedding dress to someone that is looking for a casual dress. So this is a triplet-based price, but we also needed to inform this information to inform the model about this type of property, so we added it also as a feature. Later, we wanted to improve our within-category understanding of the model. This is why we added triplets-based fashion attributes. So we added, you can see here that the positive and the anchor are long-sleeve shirts, while the negative is a V-neck shirt. So they should be in different areas in space. And lastly, to further improve our cross-category understanding, we added a special loss called arc face loss based on category prediction. And here you can see how our t-SNE improved dramatically when we added it. Okay, so we have 5 datasets. Today, so this was like just a case study of fashion, but we did a lot of improvements on our model. And today we have 5 datasets. We have textual, image, and item metadata features. The model includes 6 losses. And in order for us to succeed in several different downstream tasks, we built 5 different evaluation metrics based on cross-category, within-category, search queries, and also user interactions to improve our model, to check our model. We also had a diverse customer, and that's why we needed to use also online and offline inference. Okay, so let's have a quick look at the model architecture. I just added a simple model on the right. Here you can see that our model is actually a multitask learning model where we have 4 triplet losses, 1 categorical arc face loss I just mentioned, and image reconstruction loss. The features are text embeddings, image embeddings, and metadata categorical features, which we converted to embeddings and added to the model. When we had triplets, we actually had three of those features for each items. So how did we manage to add 3 types of triplet loss to the same model? For this, we need to understand how the triplet loss looks like. So triplets are actually, triplet loss is, what it tries to do is to put the anchor and the positive in a distance that is smaller than an anchor and the negative by at least a margin. And this margin is a heuristic number that we can play with. So for example, if I'm looking at cross categories, then the margin should be bigger than within categories, because we want all the items from the same category to be in one area, but inside it, we want to separate the small within categories differences. And so we played with this margin, and actually to have the best implementation of those 4 different triplet losses, we had to swipe and check what was the best parameter to use. Okay, so in the plot, you can see our accuracy improvements when adding the different types of dataset I just mentioned. All datasets together showed error reduction of 36% on annotated test set. And another big improvement we saw was by improving the text embeddings. As I mentioned earlier, they weren't that good because they weren't trained on commerce dataset. And when we trained them on commerce dataset, we saw a significant improvement of 26 error reduction. Okay, here you can see a nice example. So on the right, you have the anchor product, which is a ring cost $30. And on each row, you see the most similar item returned by using nearest neighbors. The first line is returned by our product embeddings, and the second row is given by the image embeddings. So you can see that our product embeddings return only rings, more or less as the same price, while the image embeddings actually return the bracelet, and also the price changed dramatically. Okay, this part is actually my favorite part, as I think this is like the most non-obvious part of the lecture, when I want to talk to you about how we could further improve inference using our product embeddings, not as product embeddings, but create a new feature out of it, and also how we can represent other entities using those product embeddings, and by this actually increasing our coverage and being able to create new signals. So we had state-of-the-art embeddings, but now we created out of them also clusters. We used k-means algorithm to create 60K clusters out of our embeddings. And this was a lightweight ranking model, lightweight ranking signals that we pushed to many ranking models, and it actually outperformed our product embeddings in every model we integrated it. As for applications of our model in other verticals, we used our embeddings to represent user and shops. Why doing it? So I think the most obvious reason is that creating shop and user embeddings from scratch requires a lot of effort. I mean, you need to build everything from the beginning. And if we can use the product embeddings to do so, we can just reduce a lot of the effort. And of course, we can do the same for clusters. We can aggregate on the clusters. Another advantage, and I think this is the significant advantage that we gained, is that now the user, shop, and product embeddings were in the same space, meaning now we can find similarity between user and a product, shop and a user, and we could use this similarity between entities in different ranking models and different downstream tasks. And that proved very, very useful in all the downstream tasks I mentioned before. So how do we do that? When we wanted to represent a user, what we did is using the recent interactions of the user with product. And when we wanted to represent a shop, we used the most viewed products of the shop. Okay, ultimately, and I personally find this impressive, shops went from an idea to a live product in 6 weeks. And finally, I want to conclude by sharing with you our main takeaways. First one is when working on ML model, we always need to iterate. So build it in a way that enables many iterations quickly. Push for rapid deployment. It's very useful to learn from user behavior, experiments, and metrics of downstream models. To do so, you'll probably need to balance between ML work and business need and understand what your customer really needs and build your timeline accordingly. And lastly, and for me, it's most importantly, be resourceful. I know it's easier said than done, but think how you can use your model in non-obvious ways, like we did with the clusters or shops and users. That's all I have for today. Thank you very much for coming to this lecture. Let me know if you have any questions or comments. Thank you very much.
And thank you. It was super interesting. It's fascinating to see the other side of a tool that we all use on a daily basis. So it was fascinating to see the others, the behind the scenes of it. So I want to ask you several questions, if it's okay. First, you mentioned several times a strong annotated data set. And I would like to ask, how did you make those annotations? We know that to annotate, it costs a lot of money, and especially if it's item that the user upload, it's not very strict and organized. So can you explain a little bit about this process? How did you get the data? What was your annotation strategy? So it's super interesting to learn how did you do that in such scale.
I totally agree that it's very interesting to understand it because it wasn't easy, and we tried several techniques, and until we got to, I think, what we believe is ideal for us. So we started actually with giving some like really annotation of 2 items to people who work in annotating. And this wasn't so good. We needed to write everything like, what do we say is similar? Like, what do we mean by similar? But then our good solution was actually using a dedicated app that Facebook have, Meta have, which called Viewpoints. And people can download the app from all around the world, and they can start tagging in tasks inside the app. So we added a new task of that, like the triplets I mentioned before. And to create those triplets, we actually used our embeddings and the image embeddings to create 3 similar items. And the user could say which item is more similar. If they couldn't decide, they can say if neither of them or both of them are similar to the anchor. And from this, we created in the end a huge triplets dataset, which was so big we could even add it to our training model, which wasn't trivial, because if we would annotate with something that is more expensive or easy or more difficult to create, then we could only use it for evaluation, which was the main purpose in the beginning.
Super interesting. Basically, you did outsource of it and let the common people to just decide what does it mean. Super fast, because in my experience, I thought that you will have to bring some people with understanding in fashion and something like this, because all those small details between items that could look the same for each one of us, but there are different categories. So super interesting. And I like how did you also approach like the business question? Once you outsource it, you need to better explain people what you are aiming for and then how to annotate that. So very, very interesting. I would like to move forward to our next question. In your talk, you mentioned online and offline inference. What do you mean by that? So how does it divide it at your work, online, offline?
Yeah, maybe it's not a common usage of those 2 words. It's very common at Meta. So there are 2 options to create the embeddings. One is what I call offline, which means we don't care when it happens. It can happen once a day. We have a pipeline that calculates it. So we can reduce the QPS, we can do it at night. It can take a long time, and this is how we can create the embeddings on billions of products. We just aggregate over day the calculation. But some downstream tasks wanted it online. What it means is like real time, actually. And then we needed a different infrastructure that Facebook created, that someone can just send the product ID, and we calculate the embeddings real time. Like it doesn't take the time, but this we can't really do on billions of products in a second. So we need to support those 2 infra tasks, and also to understand what our customers need. So if we have like a lot of people using it online, or maybe someone is using the offline and creates like huge tables we can't really support. For example, our product embedding size is currently between 64 to 128. Not between, we have 2 versions, but if it was bigger, then it's not, we might not be able to save all this information in a table, and we might need to support only online on a lot of products. So it's something that you need to take into account when building a model for production.
Super interesting. Just another quick question. What did you do when you had a new concept like Corona mask or something that's new and you need to understand very fast, okay, how do I do embedded for that? Is it something, is it a thing? So did you manage to approach those kind of tasks, or what did you do when you have a new kind of category, let's say?
Okay, that's a very good question. Actually, our model is not updating that fast. We can create a new model every day, and this is what we did in the beginning, but because we are calculating it on billions of products, then probably, we're now having a version every like few months. But when we did build it every day, then yes, we do have in our dataset all the products. I said about the arc-face loss, so the arc-face loss is calculated on all the products that we know their category. So if we have new products and their category exists and the model that calculates the category do it well, then we can add it to our model. And if not, we hope that the information we already had will be good enough. It kind of depends on the freshness of the model.
Yeah, I know. This is something that many companies or data scientists think struggles is when is the right moment to update your model, especially if you have billions of data points. So you don't want to do that too early because it costs a lot of time, money, efforts, but you still want to be accurate and be the update. So it's very fascinating to see how do you do that in very large scale. So I have another question. How can you explain the improvements of the ranking models over the original embeddings? This is a question from Guy. So we want to understand what caused these great improvements.
When you say the original embeddings, you mean the image pre-trained embeddings or the first version?
The first version.
So the first version. So yeah, so the first version had only one data set and only like 2 features. So because it's a multitask and we had it in the end like 6 different losses, the model learns from I mean, it's also they're helping each other, the losses. It's something that we see very frequently if we manage to update the heuristic values in the right way. And so in the beginning, we only had cross-category understanding. And then when we actually eyeballed the results and tried to understand where we are not doing well, where should we improve? And then we saw, okay, we're really bad at fashion. We looked at, we are just bringing everything closer to each other, all the dresses, and then we did it step by step, every time looking at what is not doing well and then improved and added more data sets and more features. Also, like other metadata information on the products improved our model, and that was also something very useful. And of course, what I mentioned about the text embeddings. I mean, we actually started with something that was very, very weak, and then there was we used an improved text embeddings, and it just improved the way what our model knows about the product. So it's also improved it.
Super interesting. Another question that just popped up. People ask if, we have the marketplace here in Israel, but we will see the shops here in Israel soon. Can you tell us more about that?
Yes. So actually, you can see it. You have it in the Instagram. When you open Instagram, there is a icon of shop. So there are shops. And also in Facebook, if there are some tabs that are hidden inside
in the blue app.
Yeah, in the blue app.
Okay.
So there you can also see shop, but I think the main difference between here and the US is in the US, they're very focused on really doing the entire buying experience inside the app. And I think that in Israel, you're still always redirecting outside. So you go to a shop, and probably in Instagram, you can shop on site, but on some of the shops, you will just be redirected to the original shop, which is not giving you the full good experience. And to be honest, shops is right now trying to understand how to perform well in the US, and they're not still improving a lot the experience in other countries. So I believe that next year you'll feel more this activity in your feed.
Okay, so we have a scoop, maybe next year.
Yeah, exactly.
So I think it will be a lot of startups, a lot of companies, a lot of just small businesses use that as a platform. You said in the beginning, you said 36% of the small business in the US, they don't have a website, and using Facebook or Instagram is a perfect. I know tons of people who use Instagram as their main lead gen for sales. So it's super amazing. So we will wait patiently. So there's another interesting question. Is the paper published? Have you published it in a conference or just archive? Can we read it?
The model?
The entire thing that you have done. Have you tried to publish it? The paper? No. Okay, fair enough.
But a good thing, maybe we'll publish it. I mean, there was a work of adding collaborative filtering inside our model, and this is something that will be published soon, hopefully, which is something that is unique. We're trying to understand from user interaction attributes of the product. But those embeddings, no, they weren't released.
Okay, great, fantastic. We have tons of questions from people who want to ask a lot of things. Yeah, people are very interested by this talk. I think once you can relate to the product and you can understand it and see, or maybe use that, so it's much more fun to ask. People were asking a good one. What is the tool that you are using for continuous integration as part of this project. I believe that you have tons of things that you need to integrate and make it work in the production. So can you elaborate more on that?
Yes, but I'm not sure it's very interesting for people not working at Meta, because everything in Meta is like something that is internal. So I can say just names, but I'm not sure it will really help anyone. So we have a tool that supports the framework of creating a model, a tool that supports the inference I mentioned, which is like the online inference. We have pipelines that calculate the model that we created on a daily basis or even hourly if we want to. And of course, there is just the backend or the code that is written, unfortunately, in www, that is also part of the play, and with some of the features created from there. And they're all integrated together. And I think that's the most interesting thing I can say, because, I mean, just throwing names won't help a lot. But we are always trying, like Facebook is improving the infrastructure all the time. For example, the infrastructure that supports the model itself improved this year, and we're always trying to work with that the infrastructure together will work well.